American Masters in Mathematics is a newly formed math competition and a festival. In this video, I will discuss a solution to the second problem. Let R denote the set of real numbers. Suppose a real function f is strictly decreasing and 2026 compositions of the function is just equal to the identity function. Part A. Prove that f of x equals x for every real number x. Part B. Prove that there exists exactly one real number x such that f of x equals x. Let's start with a notation. Fn of x is the n compositions of f. Then, by the given condition, f 2026 of x equals x for all real number x. Proof of the first part. Let g of x be f of x. Using the same notation for function g, we have g 1013 is 1013 compositions of g, which is 2026 compositions of f. So, it is indeed the identity function. Immediately, g is strictly increasing. For any x1 less than x2, because f is a decreasing function, f of x1 is greater than f of x2. The inequality sign is reversed. Applying the function f on this inequality again, the inequality sign is reversed back. We got g of x1 less than g of x2. Therefore, g is strictly increasing. Our objective is to prove g of x equals x for all real number x. Suppose not. For example, assume g of x is less than x for some x. Applying function g on this assumption, g of x is less than x, applying g, then g of x is less than g of x. G of x is simply g2 of x, and g of x is less than x according to the assumption. So we have g2 of x is less than x. Repeating this process again and again, we got g3 of x is less than x, and so on. Eventually, we have g 1013 of x is strictly less than x. But this is a contradiction. Therefore, there are no real x such that g of x is less than x. And we got g of x is greater than or equal to x for all real number x. Similarly, we can prove that for all real number x, g of x is less than or equal to x. The proof of part A is complete. Proof of part B. As a quick recall, part B is to prove there exists exactly one real number x with f of x equal x. First, f is a non-two function. In other words, it is surjective. This is easy to verify. For any real number y, let x equals f of 2025 of y. Then f of x equals f 2026 of y, which equals y. Define another function h of x as f of x minus x. It is a sum of two strictly decreasing functions f of x and negative x, and therefore is decreasing. At this point, there is an advanced proof using theorems in real analysis. F is a monotonic function and also surjective. Then it is continuous. The proof can be done by applying intermediate value theorem. In this video, I'm going to give an elementary proof that is accessible to high school students without a background of real analysis. The objective is to prove function h has one single root. H is a strictly decreasing function, so it has at most one root. Assume h has no root. Define set A to be the real numbers x with h of x being positive, and B the set for h being negative. Both A and B are not empty because both f of x and negative x are ranging from positive infinity to negative infinity. Their union is all real numbers and they are disjoint. Moreover, because h decreases, there exists a point x0. Before x0, h is positive, they are in A. After x0, h is negative and they are in B. Question: is x0 in A or B? In other words, is h of x0 positive or negative? Here comes the crucial part. Assume x0 is in A. Then h of x0 is a positive number denoted as delta. By the definition of h, f of x0 minus x0 is delta, or f of x0 equals x0 plus delta. Because f is decreasing, then for all x in A, f of x is greater than or equal to x0 plus delta. We got a lower bound of function f on the set A. What about f's values for x in B? The set B can be partitioned into two intervals. One is the open interval between x0 and x0 plus 1/2 of delta. On this interval, h of x is negative, or f of x is less than x, which is further less than the right end point of the interval, x0 plus 1/2 of delta. So, x0 plus 1/2 of delta is an upper bound of the function f on this interval. Again, because f is decreasing, then for x in the rest part of B, f of x is also less than x0 plus 1/2 of delta, and we establish an upper bound x0 plus 1/2 of delta for all x in B. Now, in set A, f has a lower bound x0 plus delta, and in B, f has an upper bound x0 plus 1/2 of delta. Then f cannot take any values between x0 plus 1/2 of delta and x0 plus delta. This is of course a contradiction because f is a non-two function. Similarly, there will be a contradiction again if we assume x0 is in B. This proof is of course elementary. But did you taste a flavor of real analysis? Thank you for watching.